Now let's move on to the second non-ideality that is also related to the on resistance of the switch. So, and to bring that topic, let me ask this question. Let's say I take the same track and hold we have, and let's say I don't have an input is 0, right? And as usual the switch is periodically opened and closed, and then I look at the output samples here. If the input is 0, what do you expect the output samples to be? 0. That's what any sane person will think, but it turns out in reality, because you are operating the circuit at a temperature greater than 0 Kelvin, the electrons in this resistor has thermal energy, so it moves randomly here and there. Random motion of charge results in random current, and this random current induces some random voltage here. So if you actually take an accurate voltmeter or something and measure it, you will see some random signals like this, the samples. And this is the non-ideality we will now look at, which is thermal noise. So the noise here is due to the resistor, on resistance of the switch, that is. So which means even if you take any resistor and try to measure the voltage across the resistor with high precision, ideally you expect it to be 0, but in practice you will see small fluctuations over 0. So that's why we call the resistor as noisy. And again, for ease of analysis and understanding, we model this like this. We assume that the resistor is noiseless, and the noise is coming from a hypothetical voltage source Vn. So if these are the terminals A and B, so like I said, say that this is the typical mindset of Indian parents. Their kid is always good. It is the friends who is spoiling their kid, right? So the same thing we'll do. We'll say resistor is poor thing. It doesn't know anything. It's because a hypothetical voltage source is there, just creating noise. So once again, this is a random thing, so you have to resort to statistics. So the mean of this noise luckily turns out to be 0, because if the mean was non-zero, we can generate a DC signal from noise without doing anything. So you just take a bunch of resistors in hand and go and solve energy problems of the world. So fortunately or unfortunately, that is not happening. So mean is 0, and if I look at its power spectral density, the two-sided power spectral density is flat. This is SVN of F equal to 2 kTr. The single-sided power spectral density is basically 4 kTr. So K here is the Boltzmann constant, 1.38 into 10 power minus 23 joules per Kelvin. T is the temperature in Kelvin, right? And R is the resistance value. But yeah, here let us say if I try to find the power in this noise signal, how do I find the power from the power spectral density? You integrate it, and if you integrate it, what do you get? Power, but if I integrate this thing from 0 to infinity, what do you get? If you integrate this, what do you get? Infinity, right? But of course that is not true, because it turns out if you go to frequencies greater than few terahertz, classical physics, classical mechanics don't hold good, blah 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 blah. It turns out at very high frequencies it drops. Okay, but of course we are dealing, our circuits will have bandwidths much smaller than that limit. So for all that matters to us, it is constant. So, good. So now we have this information. Let's try to answer two questions. In my track and hold, if there is no input, I will get some noise. What will be the power spectral density of those noise samples, and what will be the power of those noise? That's a question we would like to get answers to. And before solving this problem, let's solve a simpler problem. That is, I'll ignore the switch and then take only R and C. So here let us say we try to find V out of T, and we'll try to find what is the power spectral density of V out of T and the power of V out. Okay. Again, for analysis, we take out the noise contributor in the resistor. lump it using a voltage source Vn. So this has a power spectral density 4 kTr in single sided. So if I know the input power spectral density, how will I find the output side power spectral density? If I know an LTI system h of f, hopefully everyone knows. If someone doesn't know, you can meet me at the end. It's not that difficult to explain. So I'll directly write the input power spectral density is 4 kTr times magnitude squared of the transfer function. And what is the h of j2 pi f here? It's 1 by 1 plus j omega rc, that is j2 pi f rc, right? So if I put that here, I'll have 1 by 1 plus 4 pi squared f square r square c square, right? Just algebra, I mean nothing significant. So again, you try to sketch it to get a visual interpretation. This is S V out of f. At f equal to 0, what is the value of this? 4 kT r, right? So it starts like this, and then just this something. So now I have found the power spectral density. The next question I am trying to find answer is the power of this. How do you find the power of this? I integrate the power spectral density from 0 to infinity because it's single sided. So I'll take the constant out, 4 kTr, 0 to infinity, this thing's times df. It's simple integration, 1 by 1 plus x square. Integrated, you get tan inverse x. You put all the limit. I will not do algebra in class. This integral evaluates to 1 by 4 rc. So if you do the simplification, 4 goes, r and r cancel. We end up with this omnipresent kT by c. And of course, if you are seeing this for the first time, it should be very counterintuitive because the noise is generated by which of the two elements? Resistor. But when I find the total noise power, it doesn't depend on the resistor. Poor capacitor is taking the brunt, right? But the explanation for that is this. Let us say I go and change the value of the resistor. Let's say a resistor is reduced by a factor of 2. What will happen to the DC value? R is becoming R by 2. This is going to half. What will happen to the bandwidth here? R is reduced, so bandwidth will expand. So it will do something like this. So it turns out if you take the area, both will be same. If you change the resistance value, the low frequency power spectral density changes, but the bandwidth changes in the opposite direction. So the two effects counter each other and it's still kT by c. Right? So you will see this, if you are doing circuits, you will see this, in every place. Every time it's always kT by c. So now we have done this. Let's now look at actual track and hold. So I'll take this. Again, I'll take out the noise and show it like this. Okay. So let us say now I'm interested in the sample V out of n, which means I'm interested in the nth clock cycle. Fine. Now the noise will be added to the capacitor when the switch is open or when the switch is closed. Closed. That's when you have closed path for current to flow. So let us say I'm closing the switch and I'm interested in the nth clock cycle. Okay. Now if I look at the capacitor voltage, two things happen. One, of course, this noise voltage is trying to inject some noise into the capacitor. Second, notice that when we are turning the switch on, the capacitor will have sampled some noise in the previous clock cycle. I am looking at the nth clock cycle. in the n-1th clock cycle, it would already have taken and sampled some noise. That is going to be present as an initial condition in my current clock cycle. That is one difference between the continuous time and here in discrete time. Clear? So I'll have two things happening. One, I'll have Vn trying to dump some noise charge. Second, I'll have the previous noise sample V out of n-1 acting like an initial condition. What will happen to this initial voltage stored across the capacitor? Now it's a simple RC circuit. I have some V in, R and C. I'm saying capacitor has some initial voltage, some V0, or let's say Vx. What will happen? Exponentially. I mean, remember that now the initial condition across a capacitor, I can think of it as an additional voltage source in series. This is, let us say, V1, V2. I have two input voltages. How will I analyze? Superposition. So I will not ignore, I'll ignore this fellow. So what will happen to the voltage across capacitor? This is the voltage now, right? Now the capacitor is having some voltage. So this voltage will be non-zero. Current will flow. As current flows, the voltage across capacitor drops, and the steady state is reached when no current is flowing. So it will exponentially decay to 0. So, fine. This will be the effect of the initial condition alone. And remember, the switch is on for a duration of how much time? The clock period is Ts. I am observing for Ts by 2. So the sample, I look at it at Ts by 2. Fine. And as usual, I choose my time constant RC to be much smaller than Ts by 2. So what can you say about this term? It should go to 0. Okay. As long as I choose my on resistance so that the RC time constant is much smaller than the time for which the switch is on, this initial whatever capacitor had, that will decay to 0 before Ts by 2. So now we can quickly make one simple observation. If I look at V out of n, do you think it has any dependence on the previous output samples? Huh? If I take V out of n, nth sample of this output, do you think it has any dependence on the previous output sample V out of n-1, n-2? 0, right? So this is something you can quickly observe. V out of n has no relation, or I will say it's uncorrelated for signal processing folks, to previous samples. That means it is uncorrelated mathematically.
For this particular condition.
Yeah, if you have a good switch, RC is much smaller than Ts by 2, I'll write it. This is for RC much smaller than the time for which the switch is on. So now tell me, if I find that my output at a particular time instant has no relation to previous time instance, can you make any guess on the power spectral density? Why? Okay. Okay, that is all nice, math you remember, that's good. It's Wiener-Khinchin theorem, blah blah blah. But without knowing anything about the math side, right? It is nice to remember this, but also try to understand some logical reasoning as how we can get it. What is saying, it is flat. It is indeed flat, but without knowing any result earlier, can you make a case for this?
Whenever we add noise to each sample, like that noise, it's like we're looking at it for the first time.
Correct, that's what it means, but how should the power spectral density look like qualitatively?
It should look like the normal power spectral density for thermal noise. That.
No, two statements are correct. It is like saying sun rises in the east and I am writing right now. There is causation and correlation are different, right? Okay, let's put it this way, right? Ah.
So the output and input are, output is not the content of input.
No, there is
after a certain time.
correct. Okay.
And so then the only noise sources, there can be some noise source. Now that can be the source to cause.
I mean, there is, see, this is going to inject some noise, right?
Yes.
That is what is finally resulting in V out of n, right? The previous output sample is having no say in the final output. Okay, think about it. Let us say I tell you that if I look at the path spectral density of some signal, it has significant low frequency content compared to high frequency content. Something like this. Maybe something. It has a lot of low frequency content and high frequency content is 0. If this is the case, do you think in time domain the signal will be changing rapidly, or do you think it will change slowly? Slowly, because it has a lot of low frequency stuff. So it's going to change like this in time, some random thing. So which means if I know the signal value at some time instant t, can I make any guess about its value at t plus delta t, where delta t is small? It will be almost same, right? So if I know this, I can say with a good confidence level that these two guys are roughly same. Similarly, let us say I find that the path spectral density is peaking at some frequency, some f0, which means it has significant frequency or sinusoidal frequencies around that. So let us say I sketch a frequency sinusoid at f0. If I know x of t plus delta should follow the same relation as these two, right? If this is t, if this is delta, it is kind of having the sinusoidal component. So whatever relation is there between these two samples in that sinusoid at f0 will hold good for my signal also. I mean, that is basically the same thing as saying the two are equal. You told that two are equal because the signal is not changing so much, because the sinusoid is doing this nicely. So that is why you told, I know, the sinusoid at these 2 points are equal. So the signal at these 2 points are equal. Similarly, if the path spectral density peaks at some frequency, it is going to have significant content at f0. So even the signal values at these 2 points, to a large extent, follow the relation between these 2 points in the sinusoid, right? So which means again I can make with some confidence level how this sample is related to the previous sample. Fine. So now I am saying my signal at some time instant has no dependency on the previous time instance. I cannot make any guess about what my sample will be at delta t plus delta t if I know value at t. Which means, do you think I can have peaking at some frequency? No. No, if I have peaking at some frequency, I should be able to make a guess on the signal, right? Because that sinusoidal frequency will be higher. That's what we are saying. If it is peaking at f0.
So if it's peaking at f0, it will be having like many oscillations.
Correct.
So you will be having significant shifts in values.
See, but you can make, that's what, with some confidence level you can say, right? I will not be exactly able to say if I know x of t, what is x of t plus delta t. But because of the fact that it has a lot of component around f0, the relation of the sinusoid at these 2 points will most likely hold good for my actual signal also.
But that's the case for the low power.
Same, low, that's what, this also, yeah, same. Here it is speaking around DC. Here is speaking around this. Now in my case, I cannot make any comment about x of t plus delta t if I know x of t. Which means I cannot have any peaking around any frequency. Correct? If it is peaking at some frequency, I can make some calculated guess. Fine? So if there is no peaking at any frequency, what is the logical thing to have? Okay. That's what happens. So if you remember the results, you can prove it. But otherwise, this is the logical reasoning, right? So if I do this, the path spectral density will be white. It is not like rigorous mathematical reasoning. This is simple logical reasoning. That is very important for engineers to develop also. Right? Because I might not know relation of autocorrelation, path spectral density, Wiener-Khinchin theorem, blah blah blah. Without knowing anything, I am able to make this. And again, this is possible only if this happens. Fine. Now I actually gotten this information about path spectral density shape. Only thing pending is what is the mean squared value. And for that I have to look at how Vn is affecting my output. And that we kind of already did it. So again, loosely speaking, the situation we have is this. I have this. Instead of looking at the voltage for all time, I am taking samples of this output. That's what I am doing here, V out of n. Fine. So I already know the path spectral density for V out of t, and that basically look like this. So I already plotted it somewhere because I couldn't copy paste it. It completely messed up my flow. Somewhere I had it. Yeah, this was a path spectral density. I am plotting two-sided. Okay. Fine. This is roughly the RC bandwidth. Now I also know that if I take the area under this, it's kT by c. That's something we know. Now what we are saying is we are sampling this noise periodically at Fs. If I sample in time domain, what happens to the spectrum in the frequency domain? You'll have periodic repetitions around Fs. Okay? And let us say I have chosen Rc to be much smaller than Ts by 2, which means Fs is much greater than 1 by 2 pi Rc, whatever, right? So here this is my Fs by 2, this is my Fs. Okay, this is spaced at Fs by 2. As you see, the RC bandwidth is, is it correctly? I think I messed up here, right? Yeah, Fs will be smaller than, go here, this goes here. I mean, RC time constant is smaller, the RC bandwidth will be larger, inverted. So the RC bandwidth is much larger, right? So now if I sample it as you expected, there will be periodic repetitions. This will get repeated around every Fs. So which means you will have a lot of aliasing, right? So, and remember, after I sample, I will be only interested in the frequency range minus Fs by 2 to plus Fs by 2, 0 to 2 pi or minus pi to pi. After that, it's all repeating. So this spectrum is going to repeat around Fs, 2Fs and so on. To avoid confusion, I am showing it separately like this. This is basically the thing shifted around Fs, 2Fs, 3Fs. And remember, everything will kind of alias back in this frequency range. So this portion is coming here, this portion is coming here, this portion will be coming here. So I have shown only for 3 repetitions. If you do everything, you will find that everything will get added. That is, this entire curve will basically alias and fall back to my range of minus Fs by 2 to plus Fs by 2. Okay. So which means if I know the area under this curve is kT by c, I am interested in the variance or the noise power after sampling, which means I should finally integrate the path spectral density in this range. And in this range, the entire curve is aliasing. So what will be the path spectral, noise power now? It will still be kT by c. My point is to find the power of my discrete time noise samples. I have to integrate my path spectral density in this range after including all aliasing, right?
So essentially you make that in minus Fs by 2 to Fs by 2 will be integrated, will have a kT by c minus Fs by 2.
Correct. Yeah. Because as you see, right, the entire curve will alias back. As I have shown, this part already came, this part came, this part came. Similarly, if I do for infinite repetitions, everything will alias back and you will actually end up with the same thing, kT by c. Okay. So even the noise samples will have kT by c, and this has nothing to do with my RC being smaller than Ts. Okay. with RC being smaller than TS, as you see, within this range, the flat portion is larger. The portion that gets aliased back will have smaller things. So it will be mostly dominated by the flat portion. So it will still be flat. If RC is much smaller than TS by 2, the path spectral density is flat. Right? That's the only thing. The variance is KT by C. So this will still be KT by C even if I choose the other way like this. So here I have chosen a case where RC is much greater than TS by 2, or Fs is much greater than. Right? As you see, RC bandwidth is here, my Fs is here. So here also if I do the same thing, I see that this portion adds here, this portion adds, and the entire curve kind of aliases back. But if I look at the shape of the path spectral density, it is dominated by, so it is not white. Is that clear? So bottom line, if I have a sampling network like this and I feed an input, ideally you expect that my output contains only the input, but now we will also have some noise samples, and the variance of this or mean squared value of this noise sample is always KT by C, irrespective of how I choose my on resistance. In addition to it, I can say that it has a white path spectral density if I choose RC to be much smaller than the time for which the switch is on. And this simply we argued from the fact that if the RC time constant is small, any previous voltage that is acting like an initial condition will decay instantly. It will not affect my final sample. That boils down to the fact that I have no, I cannot make any guess about my current input sample if I know my previous input sample. Correct. Yeah, correct. Yeah, you are saying the input and the noise. Okay, so this is the real. And one last thing, typically in practice we have a differential signal. So you'll also have V in minus. Okay, so if this is V out plus, will contain V in plus. V out minus will contain V in minus plus another noise. So if I take difference between the two, I'll have delta V out, delta V in plus Vn1 minus Vn2. So each of them will have a variance of KT by C. Vn1 has a variance of KT by C, Vn2 has a variance of KT by C. So what will be the mean squared value of Vn1 minus Vn2? No, it's not 0. Remember that Vn1 is some random signal, Vn2 is some random signal. The noise here is coming because of this resistor. Noise here is coming because of this resistor. Do you think there is any relation between the noise stored in these two capacitors? No. So which means these two are uncorrelated. So the thing is, we know expected value of Vn1 square is KT by C. Expected value of Vn2 square is also KT by C. I am interested to find Vn1 minus Vn2. If you do this, you will have, yeah, I'm sure you guys know this. Let me minus 2 times this becomes 0 if it's not correlated, so it becomes 2 KT by C. So if the random signals are not correlated, you can directly add their powers. Again, we'll discuss it later, discuss in detail later when we encounter, but now we just start. Okay, let's stop here.